Okay. Welcome everybody. Welcome to the 2016 Fall Wulff Lecture. My name is Jeff Beach. I'm a professor in the Department of Materials Science and Engineering and the chair of our Committee on Undergraduate Studies. So it's a pleasure to welcome you to see Professor Gene Fitzgerald. But before we begin, I want to give you a little bit of background about this lecture series and about John Wulff, whom this lecture really honors. So John Wulff was a professor in the Department of Metallurgy, the predecessor to DMSC, from 1937 until his retirement in 1973. So among his accomplishments, he was an outstanding researcher, but he's really known for teaching and education and really defining how we teach material science and engineering really to this day. One of the most important things that he did for MIT and really for materials education in general was the founding of 3091. So 3091 was developed in 1968 and it's been taught in this lecture room for many, many years since then. How many people have taken 3091? How many are taking it now? Okay, so we've got a few freshmen in here. Are there other freshmen who are not taking it? Okay. Well, we're hoping to give you some good introduction to materials engineering today. So John Wulff was a very inspiring lecturer, an inspiring teacher. You can see him here. The camera can't quite capture him or capture his excitement. He really inspired imagination and interest in materials science and engineering, both through the lectures that he gave at MIT, but also a book series, a 4-volume series called The Structure and Property of Materials that defined how materials was taught really around the nation. So it redefined how we taught this field. The inaugural Wulff lecture was given by John Wulff in 1977. His aim was to present, or the aim of this lecture was to present an engaging lecture to the community, but really targeted at undergraduates and in particular freshmen, to give them a sense of what material science and engineering is, why it excites us as faculty, and to inspire you to consider material science and engineering as a way to go out and change the world in significant ways. And we hope that this lecture will give you some idea of that. What do we do in material science and engineering? Well, as engineers, and many of us, in fact, all of us in the faculty here are engineers. And what do engineers do? Engineers build things. Engineers build systems. Engineers build aircraft. Engineers build bridges. Engineers build transistors. But one could really argue that the most fundamental engineering is materials engineering, material science and engineering, because every complex system, every device that we try to build from components ultimately rests upon the materials. And the limits of what we can achieve and what we can achieve in these materials is defined by their properties. So really the materials performance determines what can be achieved. When we look at materials and science and engineering in our department, we look at both the science and the engineering aspect, and we do it in a vertically integrated way. As scientists, we're interested in processing of materials, how processing defines the structure of materials, and how the structure defines properties, and importantly, how these properties can be useful. We're not just interested in an abstract sense of what materials do and how they behave, but what can we do with them? How can we change society? And we also start from the other end. We try to identify the big problems in energy, in information, and health. What are the big problems? And what you often find, in most cases, you find that in solving those problems, it comes down to the materials, the properties, and the performance that we can get from them. And the big advances often come from big advances in materials. So by identifying these properties that would allow us to transform these fields, identifying the kinds of structure that is required to give these properties, and finally processing that allows us to make these materials not just at a laboratory scale, but a scale that can really change the world. That's what we do, and that's what we are about. And I think you'll see some of that today. So Professor Fitzgerald joins a long line of Wulff lecturers, beginning in 1977 with the first Wulff lecturer, who was, of course, John Wulff himself. Professor Fitzgerald is the Merton C. Fleming's SMA Professor of Materials Engineering at MIT, and the lead principal investigator of the Low Energy Electronic Systems Center of the Singapore MIT Alliance for Research and Teaching, the SMART Center. So his research interests are related to new materials, devices, and circuits. One of his most important accomplishments is his demonstration of high mobility strained silicon and the integration of useful 3-5 electronic and optoelectronic devices on silicon. Professor Fitzgerald is a practicing researcher, innovator, and entrepreneur. He's the founder of many companies, which you'll get some insight into today. But he started all of this here at MIT. He was an undergraduate got his degree in materials science and engineering in 1985 at MIT, went out, made important accomplishments, and has come back to tell us about them. So, welcome.
Well, it's a great honor to be here to talk to you today in the Wulff Lecture. And for those of you undergrads here at MIT, I was sitting in your chair a long time ago, well, not that long ago. And I'm hoping that I can relate to you by going through kind of my history and what we're able to do and what we do in material science, which is really, the story I'm going to tell you today is just what Jeff mentioned, which is really going from atoms to commercial impact. And it doesn't happen overnight. It's a different story than your latest quick app that you do. But the long-ranging impact, I think, is impressive, and that's the kind of thing that we can do in material science. I also finish with kind of what we're doing today because we continue to innovate, and we're continuing to kind of think about whatever the next thing could be, and so hopefully we'll be able to come back to you in a few years with even greater impact. So I wanted to start at the beginning, and I started thinking about, here I am, blank page, and why did I had to go back and think about why did I really get interested in material science and engineering? And that's always hard to do historically, right? Because you forget about what you were thinking at the time. So I went back to actually what I was doing in high school, and before, in elementary, junior high, and high school. And this turns out to be one of the more important moments I realized is that it's a real chemistry set. I say real chemistry set because I actually had grams of material. You know, I have kids that are in college now, and when they were young and I went back, and so what kind of chemistry set can you get? And now they give you these little things with like micro materials in there. It's like you could do little tiny amounts. You can't really achieve anything. You can't blow anything up. You can't, I was like, well, how are my kids supposed to get excited about science when you can't do that? And the best part about this kit was not only having grams of material, but I convinced my mother to go to the drugstore and buy some saltpeter for me, which is potassium nitrate, which, just by looking through old chemistry books, you could tell that, well, if I have the nitrate group, you could do things like, make gunpowder, gun cotton, and stuff like that. And so, so I think it's a really important thing to have real actionable things you can do that get you excited. And the other thing is, it gives you, in some sense, it's kind of giving you power over adults, right? You can do some stuff that makes your parents nervous, and that's all very exciting. Another thing that I really do remember this, and I don't know if you guys they still have these things, but nobody's interested in them anymore. But this was a huge thing, 101 electronic kit. And I don't know if you can see, because it's a digitized image, but it says features space-age integrated circuit, right? So that little square thing in the middle was one of the first TI integrated circuits. And I remember thinking this actually when I was playing with it. I go, this isn't that much better than discretes. Why do I care about this thing, right? But it's really telling because you're going to see at the beginning of all these innovations, oftentimes people aren't really valuing what's going to happen in the future. They can't see the connection from the thing. And as a little kid, I'm looking at this thing. I could connect up all the other things, and why is this important? And so that's going to be a continuing story. And being able to look forward and get the basics here at MIT so you can kind of look into the future a little bit is a really important thing to try to figure out why is that integrated circuit going to be really important in the future. My greatest thing I ever did with this was a plan that wasn't in the manual. I learned the magic without realizing it of oscillating circuits. And then I connected larger power source to this thing and was able to block television reception in my neighborhood. So that was really exciting. And again, power over adults. You see that? So the next thing was when I was in high school, this thing came out. It was the Apple II Plus. Now that was an amazing machine. This was high-end, man. It had color, right? Now it turns out I didn't have a color monitor, and so I couldn't use it initially. But I wanted to show you that when this first came out, you had to store the information as audio signals on a cassette player, right? So think about that. That's kind of cool when you think about it, right? Storing digital information that way. It's because disk drives, being small, the technology wasn't there. Second is the larger ones were too expensive at the time. But I guess one of the interesting things is to show you the perspective on what people were thinking about back then. I actually programmed this for a local company, and I thought, how ridiculous. They're going to buy this machine, they're going to pay me to program, and I'm going to sell this whole thing, and they're just going to use that computer to run one piece of software, right? And so I was like, why would anybody do that? But it doesn't matter, I'm going to make some money, right? So I had this beginning entrepreneurial streak, but I completely ignored it because I was really interested in just figuring out, how to program this thing for what the customer wanted. It was a personnel agency, actually. A long story what they wanted, but they wanted a database. And anyway, I was able to buy a stereo when I came to MIT with the money that I earned from that. But I didn't care so much about that because when I looked inside, I was really curious about this thing, which I programmed like crazy at the assembly code level. It's the Motorola 6502. There it says MOS 6502, but of course it's because people left Motorola and created a company called MOS, and then they got into a lawsuit with Motorola. But the amazing thing about this thing is that people had figured out how to create a depletion mode MOSFET. So they could have enhancement mode and depletion mode, and it saves a lot of power. You can shrink the device, and it's a very powerful, small microprocessor. And so I sat there and said, okay, I can do all this programming, but anybody who knows algebra can program, right? So I was thinking, what's inside the black thing, right? What's inside there? And you'll see, I really didn't think this back then, but we ended up actually affecting all these integrated circuits today. So it's really an amazing thing that MIT gave me that opportunity. So I really wanted to learn more about what was inside those things, and I went to a public high school. I think I'm still only the second person from my high school ever to get accepted to MIT. When I came here, the reason I chose course 3, you could tell from that previous slide, I was interested in electronics, I was interested in physics, interested in chemistry, and, well, material science, I could have it all, right? I didn't have to choose. I could work on all those things. And so that's one of the main reasons, actually, I really was interested in course 3. Now, here's our graduation picture. Here I am over here. It turns out that actually, how come this isn't working? I lost a lot of weight and facial hair. No, I'm joking. This is me over here, young guy. But it's interesting. We still chose to wear suits, even though this was a time period where really people didn't wear suits too much. But I guess wanted to look professional. Chi-Phi. Anybody here from Chi-Phi? Yeah. Anybody else? 32 Hereford. So I was alpha, man. Look at that. I was president of the fraternity at some point. Fools choosing me. No. So inside here, it's funny. The people you meet at MIT are. So this guy over here. If you can see my. Actually, hold on. How come? I should be able to write on this. Oh, I know what I gotta do. I can hardly see. That's a problem when you get older. Yeah, so this guy, Bill Irving, is now the Bond King for Fidelity. So Bond, B-O-N-D, right? So he was an electrical engineer, and he's on CNBC once in a while. Mike Warshawski is the CEO of a Swiss bank, interestingly enough. I mean, you got a picture like I knew these guys when, we're just trying to figure out how to eat. And so and then Mark Lambert was one of the first 500 employees of a small company called Oracle. So he doesn't really have to work anymore. And then I think well, I got to keep moving here. So it was great. I loved living off campus. And our high tech at the time was you could have terminals to go into the main computers on campus. We were a cool fraternity. We had one terminal in the fraternity so we could go into MIT campus. So we were doing this new thing to different research facilities called email. And it's really, it's just incredible, all this. Now here's the real funny one. So this is Louis Scott. He was a fraternity brother from Mexico. And what he's talking about here is a protest about tuition. You didn't even know that. See, nobody laughed. You didn't even know that that number's so small. It was protesting tuition back then, that in 1985, we were going to reach $10,000 for tuition. It's like an incredible, a huge number, right? So protests about tuition increasing have been going on forever, if you didn't know that. So some things change, some things don't change. My friend, this is Maurice Cartman. He was another material science grad, and we ended up taking a lot of course 3 subjects together, and then we also went off to IBM to do co-ops and learn about how large corporations did research. And that's a significant thing, because back then, I love this advertisement. This was in the MIT yearbook. There's like 50 corporations with R&D labs trying to define the future, doing long-term investments to figure out the future is. Hughes, which doesn't even exist anymore, I mean, Hughes Research Lab does, but the large corporation as it was doesn't exist anymore. If you look at this advertisement, it's appealing to you to help them define the future, to go out there and do fantastic things, right? You probably know that maybe there's 3 companies today, large corporations probably do that kind of thing, and everybody else is worried about quarterly profits. There's been a huge change in our innovation ecosystem, which I'll talk about from my own personal journey here. So when I entered graduate school, which I didn't know I wanted to go to, but MIT professor in course 3 told me, hey, you should really look at this. And I said, wow, stipend's pretty large, and I get to learn more, and I don't have to pay for it, right? I was a middle-class kid, so if I had to pay a huge amount of money, I would have never gone. So, but the system was the system set up by our friend. Do anybody know who this is? Nobody knows who this guy is. What? You got it. Vannevar Bush, rhymes with beaver, by the way. Easy way to remember how to say that. And he set up the idea that nation states should invest in research, which was a novel thing in the 30s. And really, if you think about what I was thinking was, I want to go to this place, right? And these were the large corporate labs. You could go there, they would fund you to help them discover things about the future, and all I wanted to do was get that white coat and do something important, really. That's what I wasn't thinking about, oh, I want to create some company and flip it in 2 days or anything like that. I was thinking, I want to go there and learn how to do something significant with this knowledge. Look, I could see those chips, I could see the chemistry, I want to do something like that and make an impact, right? And so really my goal was to try to learn as much at Cornell and then go off and join one of those places. But even then it was starting to narrow. So in the late 80s, and what was happening was a lot of the corporate labs started disappearing. So I'm going to take a brief moment here. I want you to think of something that is different. At the time when I was working here, going to grad school, everybody focused on sort of individual pieces of technology. And one of the important things you're going to see is that the reason that we were able to move forward and influence the world in what we did was that there's always some force telling us about these other pieces, which is the application and how the world works, right? And I think that if you look at great innovators, they identify the piece of technology, the science, that's critical to having a big impact through knowing a wide range of applications that are needed out there, and also how the current industry works and how the world is. Not that it can't change, but having all those things in your mind makes you focus on a particular problem versus another one. And I'm going to go through how I was pulled into that through the people that were around me, okay? And I don't have time to talk about this, but there's a lot of classes now that are appearing at MIT to talk about this and to teach this. We have some in our department, and I'm going to end talking about the innovation and entrepreneurship minor. So at Cornell, how did I get those other pieces? How do I figure out market applications? I mean, I've been in school all this time, right? Well, except for my little entrepreneurial things I was doing when I was in high school. But essentially, how do I know what the right problem is? I have to choose an advisor in graduate school, and it was really important to me because I still wanted to have that impact and build something. And so the key thing back then was, even though it was tailing off, there were still these corporate labs that overlapped with university interests. And my advisor used to go to Palo Alto in the summers to work at HP Labs, which looked in semiconductors at the future, and they were very interested in this new material called gallium arsenide and trying to use that to build new kinds of integrated circuits. And so he would come back to campus, and he was motivated by problems that he saw out at HP. Second person is Jerry Woodall. He's a national technology medalist in the United States now, but at the time he was an IBM fellow, which meant he could go anywhere he wanted, do whatever he wanted, and he used to hang out on Cornell campus, and so I ended up running into him. And there was a topic related to the two, which is how you're going to build new kinds of devices using these lattice mismatch materials. So in semiconductors up to this point in time, all the useful semiconductors in different areas were always lattice matched, meaning that if you were to deposit layers of one material on another, you make sure that the lattice constants are the same size so you don't get any stress or defects or anything like that. But it was pretty clear that those markets were getting very mature, and you could build all sorts of new stuff if you could figure out how to combine different semiconductor materials that didn't have the same lattice constant. The big one being that silicon was already the dominant electronic material for circuits. So if you could add stuff to that in some way, that'd be great. But the problem is, of course, the lattice mismatch is so big for a lot of materials you want to put on silicon, they become defective and they're not useful. So it's a huge kind of barrier to kind of going further. So that problem now is motivated by those wide range of applications, and we kind of know how things are made because I'm interacting with Jerry from IBM. And I start to focus on this problem, which is, so even though there's all these potential applications, it gets down to one thing, is how can I put one of those lattice mismatch materials on another and control the defect density, right? And people didn't really understand the relationship here. I'm showing you this, now a well-defined slip system, and people were aware of that. Semiconductors is kind of interesting. The reason that this actually becomes a problem is that at room temperature, they're brittle. They don't deform through introducing defects like that called a dislocation. So what happens is, though, when I want to deposit those materials, I have to go to a high enough temperature that they become plastic. So like metals, you guys probably know that if you bend copper, it's dislocations that are moving in response to that until finally they get all tangled up and then it breaks, right? So here, semiconductors are like that when you deposit those films at high temperature, and you have to deposit at high temperature because you're using that substrate to seed the crystal growth, and so if it's not high enough temperature, you don't get a good crystal. So you got to figure out, well, if I put a lattice mismatch material on top of this substrate, so here's the substrate and here's the layer, there's two states you could have. If it's thin enough, all the atoms go down and they don't know that they're supposed to be at their bulk lattice constant yet, and so they could be stretched to fit on that substrate template, right? But you can imagine eventually if I grow thick enough, I'm building up more and more strain energy, right, per area, and then eventually I can afford to inject in things like dislocations, because when this thing comes in, it puts a half plate in the material, so it allows the layer to relax, right? And the dynamics of how this comes in become very important. This is the thing that the dislocation sitting at the interface is what allows the thing to relax. And then this dislocation that comes up is a consequence that a dislocation can't end in a crystal, right? So a lot of times you either want to keep it very thin. In that case, you kind of know, okay, I want to not cross that boundary where dislocations come in. But you're going to see later the big advance is I want to bring them out, I want it to relax, but I don't want to have many of these things. But it's kind of a paradox because, well, I have to have that because I've put the misfit dislocations in the interface. Then you're always going to have a certain number coming up. And dislocations coming up like this, if I build devices up here, are very bad. They either hurt the performance of the device or make it unreliable. Now, it turns out, getting back to academics here, that this is kind of interesting, that when I was at MIT in material science, the metallurgy was kind of becoming an old topic, and electronic materials was the newer topic, but everybody in silicon had eliminated dislocation, so there's no need in the current technology to worry about this. So there was a class here that ended up being very important to me, but it was about to be eliminated, which is kind of interesting, right? Going to show you never know what information you're going to need in the future, which is why continuous education, online education is so important, right? So, but at the time, Sam Allen, who's a professor, just retired a little while ago in material science, he actually taught me the basics of dislocation theory, which ended up being in the semiconductor field where nobody knew it, my key added value to trying to figure out this problem, right? So it's kind of an interesting collection of little threads that led to something important. So the key thing in grad school I was able to do is to determine that you can actually manage these defects when they come in. People thought, well, if you deposit a material with too big a lattice mismatch, it ends up being lousy and then you just can't use it, right? So one of the key things with this experiment is looking down at it, what we realized is I did a little experiment saying, well, what happens if I make smaller substrate with a bigger substrate? And we can see how often nucleation is happening. Because if nucleation is only happening in a few areas, and then the dislocations are propagating a long ways to make all these long lines here, then that would be some hope that we could manage them in the future, either completely relaxing materials without threading coming up, or keeping them completely strained. What you see on the right is the same sample, is that in some areas that have no nucleation source, you can build up strain that's far above the level that people thought would already bring in dislocations. So it starts to separate the sort of thermodynamics from the kinetics in this problem. And it starts to give you ideas about how to manage and engineer. So the science leads to engineering of how you can control all this stuff, right? So that was an important enough area that people recognize at Bell Labs. So off I go to AT&T. So I finally achieved I got the white coat, you know, in the long room of all those scientists there. And back then, I still got in a time period where it's called the model, Bell Labs at that time, I call it the venture model of research. They used to give you, in my case, it's like $500,000, and they would tell you, like within 5 years, you know, discover something reasonably important, or we'll put you out to the development areas, right? So that's kind of how it works, right? So off we go. And it's kind of daunting, right? Because there's so many famous people at Bell Labs. You're kind of like, geez, can I really do something important? And there I am, a younger man, sitting there. And what I built was characterization equipment, which is kind of interesting, because this is all about material synthesis. But one of the key problems was seeing those defects in a way that would allow you to count them accurately. It sounds trivial, and I spent 8 months trying to get this well, besides building a lab. And it turns out once we had that, there was other facilities available at Bell Labs, so I could grow materials and stuff like that. So it was a well-placed investment. And the other thing about Bell Labs is that you would run into so many people from different areas. And just showing you here, I want to show you in a minute, this is Yahong Zi. He ended up being my co-inventor on strained silicon. And he was originally from China, but had escaped to the US, and he ended up going to UCLA, where he learned about the things that we wanted to build in the future. I'll get back to that in a minute, and combined it with my material science advance. This is Hans Gassmann. He came from Germany, so a very international place. And he ended up working on germanium tin and tin silicon, things that are, again, popular today, but he was the early guy who did all that work, and he became an important guy in Excelis. And Connor Rafferty, who ended up doing a startup later on germanium detector arrays on silicon here in the Boston area. So the shift here was now trying to do not the strained layer, but to put relaxed layers on top of this substrate and make it completely relaxed so we could shift the lattice constant and build new kinds of devices. And what I'm trying to show you here is that a lot of times the things you learn in the university, it's the empirical relationships that you need to get started. So for example, I think with problem sets, you tend to think like, well, I'm going to, in the world, there's going to be this well-defined problem that appears to me, and then I'm going to calculate things, and we're going to figure it out. And really, what really happens here is, okay, I've got this problem, and I understand the basic relationships. In this case, you could say, I know kind of how nucleation of dislocations are going to go and how they're going to depend on strain. And I also know the velocity of dislocation, how that depends on temperature, right? And so the first idea we had was, well, I have to have these threading dislocations coming up, but you can remember I told you that this length here is what relieves the stress at the interface. So here I have the case where the amount of misfit dislocation length is the same. But in this case over here, I've nucleated 3 dislocations, and I have many more threading dislocations to deal with, where if I use the feature that it's difficult to nucleate, which I proved in grad school, then you see if you could get this thing to propagate further, you could have much more strain relaxation, but have fewer defects coming up to the top, right? At the time, for anybody in electronic materials, because you're mostly electrical engineers, there were like, nobody's going to think about this. This is like not within the realm. So it's again the beginning of realizing interdisciplinary science and engineering. This is all kind of happening concurrently here when I was in school too. And so what you realize is that how do you create the conditions where you can keep the nucleation rate low and increase the velocity? And you can see that we did something that was opposite at the time. If I keep the stress low, which means I increment the mismatch a little bit at a time, but I go to very high temperatures, then you think that you could create dislocations that once one enters, it flies across the entire sample, relaxing all that area and preventing other nucleation near it, right? So this was actually anti-intuitive because at the time, everybody's going to lower and lower temperatures. They're developing new epitaxy equipment to try to create more and more strained materials. Here we are, we're trying to create relaxed materials, and now we have this crazy idea. We want to go back to older equipment and deposit stuff at really high temperature, right? And it turns out that it was an amazing result. What you can do is do what I'm showing there. You can create these layers, and all those black lines are dislocations. You can have massive relaxation, tons and tons of misfit dislocations being formed, but relatively few actual threading dislocations passing through the material to do this, right? And so you can see that because when you stop and grow a uniform layer at the top where there's no more mismatch, at least in this cross-section TM, you can't see any black lines threading up through the top layer. This image itself told us that, wow, we can build a silicon germanium substrate on top of silicon, and you can't create that any other way. And not only that, is now that I have a larger lattice constant, we can use the other regime, which is if I put silicon back on top, the atoms will deposit and they'll be further apart than they're supposed to be in silicon, which means they're under tension. Now the thing is, if you use epitaxy to create tension like that, you can create a gigapascal of stress, for example, and that'll change the materials properties of silicon, right? I'll show you that in a second. So, and you can't create a gigapascal of stress by bending the wafer. If you try to do that on a silicon wafer, it'll crack. So you have to use this process of by putting atom by atom, the bottom silicon germanium here is acting like little hands that are all pulling on that silicon, creating this tremendous amount of stress. And what it does is it changes the band structure of it, and it turns out electrons and holes go much faster. Of course, you know, the beauty of this is silicon is what all transistors at this time, most transistors are made of, right? So you start to realize that, well, maybe you can translate this into the application we were thinking about a long time ago. Maybe there's a way to actually change the properties of silicon ICs that are built on this. So those are good days of Bell Labs. It became a very famous thing because nobody had measured higher mobility in silicon than what was achievable in regular silicon. So both the physics community, but then there's this practical aspect which could have big commercial impact. People got very excited. And by the way, Bell Labs News, that was like to get on the cover of that is like, you know, the internal Nobel Prize or something, right? It was, you know, prize territory, right? So as a young guy, I was like, wow, this is like fantastic. And again, there's my friend Young, who's now a professor at UCLA. And of course, the manager has to be in the photo, part of corporate life. So this is the band structure. I won't spend too much time on this because I want to be entertaining and not delve into too much. But one of the interesting things was that this was so new and unusual that you could see the simple version of this, right, which is that strain is going to change the band structure of the conduction band and the valence band of silicon. But it turns out that because silicon was such a valuable material in commercial activity, there are tons of scientists that have built Boltzmann models of how electrons achieve certain mobilities in the silicon channel. And if you actually just put strain in there, it turns out none of those models work, right? So for the longest time, they kept on telling us, well, what you're talking about is impossible. And I would put transistors in front of them and say, well, there's the transistors, right? The simple idea that changes the band structure seems to be working. There's something wrong with your scattering theory, right? But what's interesting is because there was never any way to change anything, those scattering theories were held for like 20, 30 years in silicon, and people just assumed they were correct, right? So this is what happens when you have really fundamental innovation. There's many, many people out there that are taught with the old rules, and you have to tell them, and it's really amazing to watch. You could put physical things in front of them that violate what they learned in previous textbooks, and they won't believe you, actually. It's very interesting, right? And so things like velocity saturation, all these things we're gonna change because of this. Actually, to this day, there still aren't models that, this simple model explains it, but when you actually go in and look at scattering, people still can't explain it, interesting enough, even though now virtually all silicon ICs are made with this technology. So one interesting thing about Bell Labs is that the reason that a place like Bell Labs and Xerox were famous for coming up with so many of these early innovations is they really had the perfect environment for the innovation process. For example, at Bell Labs, they made everything from transistors to telecom systems, right? So I go to lunch, and there'd be people outside of the main labs, but they would be working on development in those areas that I could hear about what their problem is. So for me to figure out what technology and research would probably impact them 10 years from now was easier, right? Because they were right there living with us, right? And the other thing is that they made things. So we used to go out to Reading and look at how commercial epitaxy was done and things like that, things I needed to deposit thin films. And so you had an understanding of what was possible in real manufacturing. So it's no accident that people kept on discovering important things because they're not doing it in a vacuum, right? They're doing it in sort of an unusual environment that is really hard to stabilize from an economic point of view. So what happened here naturally was, here we were, I'm excited, and then I figured out that the emperor has no clothes. I was like trying to commercialize this within AT&T, and nobody knew what to do. And then I started thinking, well, why do people have all these research labs, but they don't ever do anything with the stuff in here that's really different? And of course, I think over time, people, instead of solving the problem, they just got rid of labs, their finances improve, and that's where we are today. But from this story point of view, I realized that things were going to change there, because if you don't have a method for commercializing the research, then eventually you're gonna eliminate it, right? And sure enough, again, Bell Labs is eliminated soon after that, or over time. So the discovery allowed me to come back, and one of the things about coming back to here was also to meet young people, because one of the things that happened, if you look at the hiring cycle, is I was one of the youngest guys always at Bell Labs, because there was nobody really hired after me. And so I was like, it's kind of depressing in a sense. So getting back to where I could be with young people to look forward and do new things with was really rejuvenating. And so back to the Institute, and we started, it turns out I had a startup package that's worse than the average assistant professor, because I was well known now, so I should be able to conjure things out of nothing, right? So fortunately, Jesus del Alamo was actually throwing out half of an MOCVD machine. So I grabbed that and figured out how to finish it. And we started with 1 inch. This is like a really old MOCVD. So we used to work on 1 inch squares, okay? So talk about moving along. I'm going to tell you, hopefully, in a little while, what we're doing now in Singapore. We're working on 200 millimeter wafers in really state-of-the-art stuff. And then here's Shri again with another grad student of mine, one of the first ones, Mayank Balsara, who later is my co-founder of the first company, Amberwave. And he's actually right here. Mayank, raise your hand. He's now chief scientist at Sun Edison Semiconductor. He's convinced him to let him still live in Boston, even though they're in St. Louis. So Mayank is that kind of guy. Important guy. So, but the one problem is that we got to get rid of that and put Boston in there. He's still a Yankees fan, unfortunately. So, and I always like this picture. This is Mayank again, but it's Andy Kim and Ken Wu. They all look like, wow, this thing's really working. What do we do now? They're kind of just standing there, but it was an early day in my group when we started small. I have to skip a bunch of stuff, but eventually Mayank graduates, and you can see the economy changing, and there really wasn't anything out there that really made sense for a guy like with Mayank's talent. So we said, hey, we've got all this new stuff. By then, the industry still wasn't embracing strained silicon or a lot of this lattice mismatch stuff. So we said, let's go do it. You know, it was almost, you know, with not enough knowledge about really how hard it's going to be, you know, same story, right? Kind of go out there not really knowing. So Mayank and I formed a company called Amberwave when he graduated. And one of the big challenges was, well, how do you commercialize this stuff? Because there aren't, if you go to large semiconductor supply chain by that time is huge, right? People making lots of circuits. You can't go to a material supplier and say, make 10 wafers for me, right? So we had to search around and find sort of specialty places that were growing and try to convince them that they could grow with us if they could produce stuff and work with us. And that was really a very interesting experience, and we learned how to work with medium-scale producers to create the technology, and it had to be much better than we did in the research lab, because now it has to go into a silicon fab, and we really didn't know how we were going to make it smooth enough so it wouldn't be rejected by the characterization tools. But at the end of the day, we did all that, and then there was 3 markets we were going after, and again, you can't tell at the beginning. It's such a basic thing. You can apply it to several different areas, but one of the early places that in the digital space was willing to work with us was AMD, actually. So one of our proudest moments here is with 7 people in the company. We signed a deal with AMD, and we're able to ship them wafers. If you look on here, it says AMD or bust, because really at this point, if these wafers didn't work, we were going to be finished. This is in Woburn, by the way. Woburn, as you know, now may change with the engine thing that MIT just created, but Woburn is the place of you know, the sort of startup slums for MIT, right? It's because there's so much contamination of land there, you can't use it for anything else, so startups go there, and rent is cheap. And so, but you know, if you look at what a small group of people did, we were able to get this through their flash fab, which is really sensitive to any impurities and things like that. And to this day, this is really an amazing thing. So we built a 25 nanometer physical gate in 2003 because people didn't believe. Now you have strained silicon, you build larger devices, the next thing they say is, it's not going to last. When you make tiny ones, it's going to go away. We go, why? And they go, we just think so, right? So you have to go prove it, right? So we did this 25 nanometer thing, and of course the thing operates faster, and it turns out, by the way, this is the last profitable node for most manufacturers in silicon today, right? So we're doing technology beyond this, but the cost per transistor goes up from 25 nanometer transistor as you make them smaller. So what's really cool about this is that back in 2003, we didn't know it, but we actually built sort of the end of roadmap device in planar form, and really quite an accomplishment. So the other thing is during this time, one of the important things for creating value is to believe in that glimpse in the future. I mean, you're only these few people, and you say, you know, it's easy to say, oh, we're going to change this, we're going to like beat Intel, we're going to do all this stuff, but you actually have to prepare for it and believe you're going to do it. And this is one of my, you know, we created a huge patent portfolio to protect us, which is again, you really have to believe when you spend all those resources, because it's very expensive, that you're really going to do it. And what we discovered was that we were building circuits in strained silicon that are going to have fundamental different properties for a long time. And the future would be different, that the layouts for the circuits would be different because the PMOS, NMOS would end up being similar sized transistors. And that's a big deal in circuit design. And so we started realizing we can sort of repatent all of silicon technology, right? So later on, Intel, this is one patent they really tried to destroy. But another Course 3 story is Nicole Garish is the co-inventor on this. So she was a Course 3 student that used to come into my class. She'd sit in the back. She'd wear a cap, baseball cap, because she just rolled out of bed. And she looked like she wasn't listening to me, and she'd ace everything, right? So when we started Amberwave, I knew she went to Draper. And I went over there, and I stole her back out, so my friends at Draper got mad at me. But she joined the company and ended up being in charge of our intellectual property group. And one of the cool things, we had projected kind of ultimate power savings of like 50%, which is fairly accurate to what happened. So you really have to believe and kind of protect yourself. Intel was first to market, and I don't have time to go into the story, but they eventually licensed our strained silicon, which is a huge deal for the company. And then later on, TSMC, which is the foundry in Taiwan, to have parity in technology, bought most of the portfolio. So there's a press release. You'll have a hard time finding this on the web, by the way. Intel controlled the press release and really didn't like this too much. So I'm going to go quickly through a few other examples because I want to finish with talking a little bit about what's happening in material science. Actually, I'm going to skip these. There's a couple of other startups that we did, and I don't have time to talk about them. But one of the things is when you give talks like this for young people, I always, and people have asked this, I always get a feeling, a lot of times they just don't even venture into trying to do all this stuff because they think about work-life balance, which is really important. But you can do it. It's just that, notice I'm having a lot of people I work with. I'm not doing it all myself. I've got my students and employees and then other collaborators, right? So I think the thing to realize is that innovation is a social activity, actually, right? Which we often don't talk about. And you can actually achieve quite a bit if you recognize that up front. So I do have a wife. That's her. She's wonderful. And we ended up climbing this mountain in Hawaii, hiking up this volcano in Hawaii recently. And I have two children, that Danielle and Patrick. Danielle is a chemistry major at Holy Cross, and Patrick is a mechanical engineer at Drexel University. And they do know who I am, and they like me. So what's happening today? So it's just a brief interlude. See, I woke you guys up. You can have a family. That's good. And the thing is that what we're doing today. So Moore's law has stopped, just like we predicted. People thought that we were going to extend it by putting 3-5 materials, like gallium arsenide, into transistors. But we took a different approach, where we said that silicon's great and 3-5s are great. If we can combine these materials with all of our knowledge we accumulate over this time, and we could actually have it transparent or opaque to the circuit designer, we could build new kinds of ICs, right? It's just putting more flexibility into circuit designers' hands. So that's the big vision that we ended up having. And the thing that's different about this is that, remember that all during Moore's law, where the industry knows where it's going, it's the application end that determines what you do in materials and stuff like that. When you reach the end of that road, the thing that's really different is a chicken or the egg problem, because yes, we want to create these platforms, give circuit designers more capability, but the markets for these things haven't been defined yet because those circuits haven't been created yet, right? So you're kind of back to kind of the beginning stages of innovation where the markets haven't developed yet. So kind of saying that we're going to have new materials in this new world and that those platforms could define new circuit innovation is a much harder problem. And what you realize is that you have to build a research program where you have material scientists working on materials process and devices and circuit design, all affecting each other simultaneously, which is impossible to do in the United States. There's no way you can create such a program. However, MIT having some unique things going on. We have something called SMART, which is Singapore-MIT Alliance Research and Technology. And so we ended up winning 1/5 of that program to do this. Any Singaporeans in the audience, by the way? Yes. Great campus next to NUS, right? And 1,000 square meters to go do our thing, right? So, and for you, the great thing about working in other countries, you learn about culture and food. And so I'm going to make you hungry now, because see, Singapore is all about food, right? And we have laksa. Bet you guys missed that. I just like destroyed your day. And misia, right? So there you go. So besides technology, there's lots of excellent things to have in Singapore. The bottom line is we were able to build infrastructure. If you see these pieces called SMART, those are pieces that we could build that now allow us to bring this kind of big vision together. To give you an idea of how this thing was set up from the beginning, a regular silicon process goes the following path. You have a wafer, it goes through what's called the front end in a foundry, and then it goes into the back end, and then your chips are finished, right? So what we're doing here is we're going to work with real foundries in the research process. We have to make it look like we're a customer. So this is like a real big innovation, both at the research stage, but also to affect commercialization at the other end of the process. So we ended up building these two pieces, and because we have a separate line coming in here, and then we join them in SMART, we then process the unusual parts of the wafer, but then send it back to the foundry so that it looks like it never left, right? So the manufacturing facility isn't doing anything different than what it does today. This is huge because, first of all, it allows us to build real circuits in a loop with materials people. The second thing is it shows you what the new business model is for the circuit industry, which is that you can essentially today build an Intel that produces novel circuits with their own process, but they don't have to invest in infrastructure, which means that the capital return for such an enterprise is going to return to the early days of silicon, which is a really exciting proposition. So I'm going to have to skip all that, but this is our test chip. So when I was in grad school, we used to dream about having some sort of silicon design environment where we could put these kinds of exotic materials like 3-5s together with CMOS, and here's the real thing that is going to come out this year. Now that we can this is more resolved and we can see how it's going to be commercialized, we created the first foreign company that I've ever been involved. I never founded a company in a foreign country before, but with MIT and all these international relationships, we're starting to get experience with that, and so we formed a company called New Silicon. Again, a little hubris there, New Silicon Private Limited. And so we're going to follow that model I just talked about in parallel to finishing our research in Singapore. So let me finish with talking about kind of a big picture stuff in education now, where I've been using these words like material science and engineering, and then innovation. And Vannevar Bush again here wrote a famous thing called the endless frontier, right? Which is that there's always new ideas. We're always going to keep on advancing. You should always invest in technology and research. But what's interesting is, remember I was showing you those elements for innovation that are important besides just studying the technology piece alone, right? And what's interesting is we're really coming full circle, because Vannevar Bush, with the rise of things in the 30s and 40s, found it necessary to define what an engineer is. So I think sometimes when you come to school, you think like, well, it's always been a certain way, it's defined a certain way. So it's very interesting to go back and look, and I'll read this. So this is Vannevar Bush in 1942. The engineer was not primarily a physicist or a businessman or an inventor, but someone who would acquire some of the skills and knowledge of each of these and be capable of successfully developing and applying new devices on a grand scale. Today, we would call this an innovator or an entrepreneur, right? But remember, that's a standard definition he's trying to create for an engineer, right? So what you look at in my career is we went from an age of super specialization at the end of a particular wave, and then when I started going through Cornell, remember how interdisciplinary science was the big thing, interdisciplinary fields in the technical realm, right? You start to look at what we call innovation today is really just folding in other elements that an engineer used to practice, because we're headed back to a time where we need to innovate on a scale we haven't done in a long time. Things are a lot less prescribed. And so what's valuable today is to have not only interdisciplinary science and engineering, but to also be interacting with that social process. How do you know what the real applications are? How do you know what people are doing today? If you ignore those things, you can't restart real innovation in any field, right? So there's a big shift occurring. Some tools that you can use. We've been online from the very beginning with edX class, talking about the innovation process, just how these elements work together and how you can de-risk things. And Andreas Wankerwall is here, over here. So he helps me out with all of our innovation work. And the other thing, this is expanded into MIT last year, got the Innovation and Entrepreneurship minor. Are you guys familiar with that? It's a new minor that you can take that talks about, essentially, when I talk about innovation, really, like I said, from an engineering perspective, it's just large-scale problem solving. It's how do you solve this problem in a real way? And so if you're interested, you should look at this new minor at MIT. So finally, I just wanted to summarize that these classes in course 3, but venture engineering is a core class in the innovation entrepreneurship minor. And then if you take that minor, we have a class you can take that set us as 3.086. That's where we spend more time with you going through how you do this innovation problem, how you can avoid going down dark alleys and earlier in the process, and how you can increase your chance for having impact. And I'll stop there and answer any questions that you might have.
Well, thank you, Gene, for an outstanding talk.
Thanks.
Do we have questions in the audience?
So I was wondering, you had mentioned that when you came out of college, the corporate lab was the big centers of innovation. Where would you say now is the future of the big centers of innovation? Is that startups? Is that academia? Is that somewhere else?
Yeah, so the question, if you didn't hear it, was, and it's a really good question because it's the obvious elephant in the room, which is that if you look at the story, a place that I was able to innovate and learn about that was Bell Labs, right? So these corporate labs were around, and it made academia's life easier because we could even do forward-looking things here, which is just preparing the student how to think in those areas, and they could go innovate in those areas. And today, what's happened over time is, of course, there's a gap between corporate time horizon and then universities were asked to do the entire thing, right? And clearly, the university can't because it has other goals, right? It's got educational goals and things like that. So it's a great question, right? What's going to happen, right? Well, I can tell you that if nothing happens, you'll continue to see productivity decrease, and you'll see lots of public investment over here, and it'll be very difficult to have people have time to figure out how to produce real innovation on the other side, right? So, what do I think will happen? I mean, startups, if you look at startups, the startups that really produce things that added to productivity in the economy, they're in some way tails still of a lot of that early corporate work, right? The other startups that have success are really the finishing of this sort of information age paradigm that we've been in. So, it's sort of this new thing. How do we find the new thing? How do we, get a new Moore's law to kind of change things? And it's going to be very difficult for a startup to do because just the resources involved, right? You're going to have, especially, I mean, this gets kind of complicated, but you can already, I used to say this all the time, capital costs have to go up, right? And they've gone up a lot recently. And historically, 5 to 7% short-term rates are normal, right? In that world, you have to have a lot of profit to invest in the future. It's the only way you can do that, right? So I think the answer is going to be probably that you'll have, in this consolidation phase we're going through, I think, a few companies in each sector that are going to have dominant pricing, and then as capital costs go up, they're going to probably look out into the future more because they're going to have the resources to do so, and they'll spend money on R&D to preserve their future. And that's the only thing I could see because you know, this sort of longer term, you know, chaotic thing, startups can't last long enough to cover that time horizon, right? So in a weird way, trying to figure out how to get corporations to invest in the future again for their own preservation, but more importantly, there's all sorts of spillover effects that are really important for innovation, right? And so in a weird way, you want companies to look forward and spend towards the future because it helps create competition ultimately, right? So, but I think nobody really knows. That's the key issue looking forward.
Do you have any more questions?
Yeah, when you were talking, you said that there was 3 companies, or there's a few out there that were not really in it for profit.
Well, I said for profit. I said that invest in sort of larger scale innovation. Is that what you mean? Yeah.
What are they?
Well, probably the one that practices the. If you look at those elements that I was talking about for innovation, they'd be corporations that don't mind investing in markets that they're not in today. They don't mind going into new technology, and they don't mind changing business models, right? So you have to look at companies that invest in internal projects with that in mind. And there's very few of them, but the number one was Google, right? Google will invest internally in ways that they'll go into different markets, they'll go into different technology, and they'll change that thing. If they're successful, can change business model from, you know, whatever business model they're in. So they're one of the few companies that practices that, but there's very few.
Do we have one more quick question?
Yes.
So a lot of your work focused on like information technology, and we've seen like really rapid progressing movement in that in like the last like 20 years.
Movement in what?
Like we've seen a lot of advancement like really rapidly. Do you
Yeah.
think there'll be something different that like is really rapidly changing in like the next like 10, 20 years?
Yeah, so one thing that's clear, and it's a guy that ended his career at MIT, a guy named Thomas Kuhn, wrote this book called The Structure of Scientific Revolutions, right? And so he's the guy who came up with the original term paradigm shift, right? You can go read his book. He's a philosopher physicist, so it reads like a physicist philosopher, so you have to be patient with it. But you know, one of the things that is a fundamental of looking at these shifts that occur is that they will always occur. So there's always these points where people think like, you know, nothing's ever going to happen again, right? So it's guaranteed something will happen. And the other thing is you can't predict ever when it will happen or what area it'll be in, right? So, but I think you can see things, you know, I think in information systems there has to be some sort of new thing that happens. I mean, I'm trying to play my own little role in it with our collaborators in SMART in that way. But, you know, there probably something has to happen there. And obviously people have been waiting for something to happen in sort of health space, if you want to call it. And I think, you know, you'll probably see more and more devices in medical technology that really probably at some point take off like an exponential. So the other thing is, you know, just for my own needs, because I don't mind drinking cocktails, is that, you know, I think buying organs in the future is going to be a big thing. So if you can create livers, you know, create a heart, you know, whatever, and pop it into me, we're good to go. And people will buy multiple things, right? So you can see some sort of exponential thing. It affects people's lifetime. You get a feedback loop. So for sure, once we can start growing organs, it's another. So there's some things you can see that have the properties of a paradigm, but it's really hard to tell. Really hard to tell.
Okay, well, with that, I think it's a cocktail hour. So let's thank Professor Fitzgerald one more time. And thank all of you for coming, and you're all invited to attend a reception right outside right now.